Okay, we're going to try and do a video just now to prove Pythagoras' theorem. So you're going to get this question, just like it's given here, to prove that a right angled, or prove that in a right angled triangle, at a square and a hypotenuse is equal to the sum of the squares of the other two sides. And this is, I guess, one of the more difficult proofs to learn off or rote learn. So it might be better off just trying to actually get a logical set of steps in place to try and remember exactly how to go through this. So we're going to be given a triangle, and you can write out the word triangle, or you can just draw the symbol for a triangle, and it's going to be triangle ABC. That means that the vertices will be at A, B and C, the corners. And to prove that one side, so the square of one side, is equal to the sum of the square of the other two sides. So I'll say that A squared is equal to B squared plus C squared. You could also say A squared plus B squared equals C squared. In either case, the side by itself is the longest side. Okay, the construction for this is going to be the most important part of this. Sorry, there's a bit of damp on this. So the construction for this is going to be you drawing a right angled triangle here, and we're going to draw a line. So this is going to be my initial right angled triangle. We'll call it ABC, and we're going to draw a line from the top point, point B, straight down to the line at the bottom. So this is going to be my triangle A, B, C, and now we're going to draw a line from B straight to the bottom. So it's going to go perpendicular from line AC. So in other words, it creates a right angle here. Okay, and what we've created now is similar triangles. So triangle ABC is similar to triangle, I'll just label this D, similar to triangle ABD, which is also similar to triangle BCD. And just, I suppose, to explain that a little bit more, let's just say this is 22 degrees, just to give it a degree. And that means, so this is 22, this will be 58 degrees, and this is my 90 degree angle up here. So if this still is 22, then now this has to be 58 and this is 90. And again, this is 22 now because this is 58 and this would be 90. So that means that the three angles in all three of my triangles are the same, which means they're similar triangles. And we know some things about similar triangles. We know that ratios, or the sides go up at the same ratios in similar triangles. So I'm going to try and draw these three triangles over here now nice and neatly. So these aren't going to be to scale, these are going to be just as good as I can do here. So they're going to be three triangles looking the very same. So this whole proof is going to be based on this construction. So the construction is actually more difficult than the proof. Okay, and we can, it's obvious enough which is the right angle in each one and which is the narrow angle in each one, okay? And I'm going to just label these up here now for you. So this first triangle up here is the initial triangle ABC. So the right angle is at B, so that means B is here. The smaller side is C here, and the long side is A is down here. So AC being the hypotenuse. Okay, let's take the next one. So the next biggest one, here's my right angle here, right at D, so I'll label D down here. The short side is up to B, so this is B here, and it goes back to a point A here. And again over here, so here's my right angle at D, shorter side. Now shorter side is going to C, and it's going back to that point B. Okay. And going back up to my proof, I'm trying to prove that A squared equals B squared plus C squared. So this being my initial triangle, my longest side, this one here, must be A. Just label that up A, and then either of the other ones. So I'll label this B and this C. And just for this proof as well, you'll need to be able to just put some sort of a letter value for this side here. So let's call that, so we've A, B and C done, so D, and you'll see I'm using the small letters for this, and E. Okay, for these two sides here. There's no need to label up this side here. It won't be used for the proof. So just fill in the letters exactly as we, so just try to put the corresponding sides up here in these diagrams. So this is A here. The side between A and C is A. Between A and B is B. Small b, and this obviously must be C. Now this triangle here, we are not going to label this side. Between A and B now, A and B is B. Between A and D is side D. And again, finally for this triangle here, the side between, so D and C is this one here, that's E. And the side between B and C here now is C. So that's everything labeled up, okay? And you just need to know one thing about similar triangles. So we know that, sort of prove now, we're going to just write that triangle A, B, C is similar to triangle A, B, D, which is also similar. Let's put the three of them together. Similar to B, C, D. Okay, I'll just put as construction because it is as shown in the construction. And we know that in similar triangles, the ratios are the same. So let's just take the angle here. Let's take one angle here. So we're used to dealing with labeling up right angle triangles using, let's say, the opposite and the hypotenuse and stuff. So let's just try to make the side, the side B, this side here. So B, the subject of a ratio. So we have side B here, and there's also the side B here. So here let's call it the adjacent, and here will be the hypotenuse, HYP. Okay, and the adjacent here. So I'm going to the ratio of adjacent to hypotenuse on two similar triangles. So on the first one, my adjacent is B and my hypotenuse is A. And on the second one, so it must be the same ratio because they're similar triangles. So my adjacent is D and my hypotenuse is B. And that's equal to B squared. So cross multiply, B squared is equal to AD. Just put similar triangles. Similar triangles ratio. Okay, we're going to do the same now to another side. So let's do side C now. So let's try and make that the subject. So C here is the opposite, let's call it. Just go from this angle here, just to give us a reference. So C is the opposite, and C here is the hypotenuse down here. So there's no C in this one, so I can't use this one again. So C here is the hypotenuse. So let's go opposite over hypotenuse now. And that's going to be, my opposite here is going to be C over my hypotenuse is A. And that's going to be equal to, over here we have the opposite, which is E, over the hypotenuse, which is C. And that's going to be equal to C squared is equal to AE. Okay, and they're again similar triangles. Ratio. So now let's write out everything we have. So let's write, well, let's try and keep these two things that the left-hand side and let them equal to, well, the two things they're equal to. So b squared plus c squared is equal to AD plus AE. And if we go back up to the initial diagram, we could say, I'm doing overkill now, so b squared plus c squared is equal to, let's factorize out a here, so a brackets d plus e. So a multiplied by d plus e. And if I go back up to my initial diagram, I'll see the limit of d here is here, and the limit of e is this here, so d plus e is actually just equal to a itself as well. So again, just write that here, so d plus e is equal to a. Again, so you can just say in construction. So b squared plus c squared is equal to a squared, and you can just write your next line down, or just q e d. Okay, I hope that helped.